Okay, this little video is about proving trig identities using the Moivre, and you will see that asked in the question. Usually they will say use the Moivre to prove the following. So when you have a question like that, you always start the same way. So you start using a general complex number in polar form. So we start off with cos theta plus I sine theta. So you write that down no matter what. If they say use the Moivre to prove any trig identity like that, always write that down straight away. Now then you put that to the power of something, and that depends on what is multiplying the theta on the left hand side. So in this particular case it's a 3, so we're putting it to the power of 3. We then expand that cos theta plus I sine theta using two different methods. So we're going to use the Moivre and we're going to use the binomial. So the Moivre is the easy one, and the Moivre, of course, came up with this method, but also I think it was Newton came up with the binomial method, and we're going to use that as well. So we're basically finding the answer to the cube of that complex number two different ways, and of course they have to be equal to each other, even though we've just approached it in with two different methodologies. So that's what we're going to do. So the Moivre is easy. You just bring the 3 down and multiply the angle. So cos 3 theta plus I times the sine of 3 theta. So that's the answer. The Moivre really simplified this for us. The binomial, we expanded using the binomial theorem. Now, of course, because it's only a cube, you could probably do it in your head using cube the first, 3 times the first squared by the second, and cube the last. 3 times the second squared by the first and cube the last. But either way, you can use the formal expansion of the binomial, or you can do it in your head. It's up to you. However, if it was to the power of 4 or something higher, then you just need to have that method known. So I'll do it the formal way. So it's 3c0, all right, the first one by the second one. Okay, first one by the second one, and this is 0 and this is 3. So to the power of 0 to the power of 3 plus 3c1 again, and this will be cos squared theta, and this is I sine theta to the power of 1 this time. Now this is going to take a little bit of space, so let me just continue with that. Plus 3c2 cos theta and I sine theta squared, and I'm just going to go to the next line because this is not the easiest one to do on this platform. So 3c2 cos theta and I sine theta squared plus 3c3 cos theta to the power of 0 and I sine theta to the power of 3. Okay, so that's both sides done. Now we just need to simplify both sides for our convenience. So continuing with this one then. So on the left hand side I have cos 3 theta. I don't have anything to do with that yet because there's nothing to do there. On the right hand side, let's simplify this. Well, obviously we're going to have anything to the power of 0 is 1, 3c0 is 1. So I'm just going to end up with cos cubed theta there. And on this one here, it's going to be 3, and I'm going to go 3 times cos theta squared sine theta, and there's an I next to all of that. The next one is plus 3c2 is 3 as well. I squared becomes minus 1, so in fact that's a minus 3. So we end up with minus 3, and I'll just make that a little bit smaller again there. Minus 3 cos theta sine squared theta. And then the last one, again, lots of things will cancel for us. That's 1 and that's 1. And I cubed is minus I. So that becomes a minus sine cubed theta I. So now I have a complex equation, and any complex equation, the left obviously is equal to the right, but even more so, the real bits on the left are equal to the real bits on the right. Now the real bits are the parts that have no I in them. So on the left hand side that's real, on the right hand side this is real, and this one here is real. And we can also say that the imaginary parts, which is the bits that have I beside them, they're also equal. So you can generate two separate equations using this one larger equation. Now, which are we working with? Are we going to be working with the reds, or are we going to be working with the greens here? Well, let's go back and check what we were given on the original equation. We were given this one here, the cosine of 3 theta. So therefore, the cosine on the left-hand side is the red. So we're dealing with all the reals to generate what they want here. So let's do that now. So cos 3 theta on the left is equal to cos cubed theta minus 3 times cos theta by sine squared theta. I'm ignoring the green completely. I don't need to do that at all. If, however, I were given one where it asked me to prove sine 3 theta was equal to something, I would obviously ignore the red and work with the green. Now let's see, how close are we to what we want? Well, the original equation at the very top, let's have a look at it here. So let's have a look and see what we have and compare it to the original equation. You can see where the arrow is at the top of the screen that we have cos 3 theta is equal to 4 cos cubed theta minus 3 cos theta. And you can see what we have. We have cos 3 theta is equal to cos cubed theta minus 3 cos squared theta sine squared theta. So it's very similar, but not quite where we want it yet. So the black sheep here in my equation is this sine squared theta. I shouldn't have any sine squareds in it. So this is where we go now and go to the top of our log books on the first page on trigonometry in your logbook. And you'll see at the very top of the screen, and I'll do it up here at the top section of the page here, we're told that cos squared theta plus sine squared theta is equal to 1. Now that comes from the unit circle and Pythagoras mixed in together there. So if that's the case, what's sine squared equal to from that? Well, sine squared, bring cos squared over, 1 minus cos squared theta. So I'm going to use that here. And that's one of my favourite trig identities. You use that quite a bit in mathematics, so please remember it. So I'm going to change this. The cos cubed is fine, and the 3 cos theta is fine. I'm going to change that to 1 minus cos squared theta. And that gives me cos cubed theta, and if I multiply this out, I get minus 3 cos theta, so that times 1, and then minus 3 times minus is a plus 3 cos cubed theta. And adding that up, I get 4 cos cubed theta minus 3 cos theta, which is exactly what they wanted us to prove at the top of the page. So I'm just going to write QED there, meaning quadratic demonstrandum, job done. Now here's another one that I have chosen for you to do by yourselves, but I will start you off. So remember what I said, always start with the cos of theta plus I times the sine of theta. And the power depends on what's beside the theta on the left hand side, and this is a 3. Exactly the same as before, you now continue. You use your two methodologies, one the Moivre and the other the binomial. But this time, you're going to equate the imaginary part with the imaginary part. And don't stop until you end up with what you have at the top. So best of luck with that, and let me know how you got on. Now, I have one more question I wanted to do with you. I found it online and I thought it was an interesting question. But before I do it, I wanted to guide you to that first page on trigonometry again. I already mentioned this one here for you, and it's in your logbooks. You can find it, I think it's page 14, it's the first page on trigonometry anyway. But I'm interested in these three sections as well. for the next question that I'm about to do with you. Now, the cos of a minus angle is the same as the cos of an angle. Now, we call that an even function when that happens, but I wanted to show you why. So on the diagram here, we have angle A, and now I'm going to put in minus A. So there's minus A. Why is the cos of A the same as the cos of minus A? Well, the cos is the x-intercept. So there's the cos of A, and there's the cos of minus A. And as you can see, you end up in the same spot on the x-axis, so that's why they're equal. We call them even functions. An odd function is when that doesn't happen. So on the diagram, the sine of the angle is on the y-axis, and the minus A, here it's touching the unit circle, is on the y-axis. And as you can see, they are opposites of each other, so we call that an odd function. So let's use that now in our next question. So if this question came up in your Leaving Certificate paper, you might be a little bit bemused by it or even anxious over it, but it's actually not that difficult. You are told what z is. It's cos theta plus I sine theta. So very simply, replace z with what it's equal to, and you've passed the question on that alone. So cos theta plus I sine theta to the power of n, plus then we have cos theta plus I sine theta to the power of minus n. And I want to show that that's equal to 2 times the cos of n theta. So again, we're going to be using the Moivre here. Now, whenever you're trying to prove something, it's always best to work on one side and keep going until you get to the right-hand side. So I'm going to work on the left here. So if I have cos theta plus I sine theta to the power of n, using the Moivre tells us that that's the cos of n theta plus I times the sine of n theta. And the exact same with negative numbers, so that's the cos of negative n theta plus I times the sine of negative n theta. And I'm going to work on that until I get what's on the right-hand side. Now, here is where we're using what I just showed you a moment ago. So cos n theta, we won't do anything with that. And I times the sine of n theta, don't have to do anything with that. But this one here is the cos of a negative angle. And as I've just shown you on the previous page, the cos of a negative angle, well, it's the same as the cos of the positive version of that angle. So that's equal to the cos of n theta. However, that's not the case with sine. The sine is an odd function, and therefore, so this one here is going to be equal to minus I times the sine of n theta. And I have to show that that's equal to all that stuff there they have on the right hand side. Now let's see what happens here. Well, the signs cancel, which is great. And then I end up with cos n theta and cos n theta, which of course is 2 cos n theta is equal to 2 cos n theta. And look how simple that was. It's something that looked quite difficult when you first saw it.